Hi, this is the second part of architecture of machine learning systems. In the previous episode, we focused on gathering functional and non-functional requirements that you need to make decisions. Now it's time to make them. Before we get into how to do this, let me make a recommendation. Consider not having a dedicated architect or technical lead in your team. Instead, involve multiple people in this work, even if one team member has all the relevant skills. There are several good reasons to distribute the architecture work. The exchange of knowledge. Decisions are usually made in more qualified way because the teams always knows more than a single member. People involved in decision-making process usually feel more responsible for the implementation. And the risk of somebody not being aware of the decision made is less. There are also some drawbacks in this approach you should be also aware. First, you need time to discuss. And second, you need a way to resolve conflicts if several team members have different opinions how to solve particular problem. So as soon as you need to do a piece of architecture work, I recommend you to delegate it within your team, but not always to the same person. You probably have people who are good in certain areas, so delegate the management presentation to one, the data science issues to another, and the API description writing to a third. If you need to make a decision, schedule a meeting, if one meeting should be enough, or form a working group if the decision requires some research. You do not have to include all the team members, especially those who are not interested or are doing something completely different. Involve only the key know-how contributors and the people who want to be involved. So consider taking architectural decisions in team. Let's discuss what usually needs to be decided. Remember our example where you have a scoring model and need to integrate it with CRM, loan application, and fraud detection components. Usually, you are dealing with one of two situations. If it is your first model to integrate, you need to decide the type of model you are implementing, a service, a library, a function within your Spark cluster, or something else, how your model integrates with other components, and technologies and tools you use to make it work. Programming language, frameworks, runtime environment, quality assurance tool, deployment, third-party service, and way more. The second situation is simpler. You decide to use a particular technology or tool to solve a particular problem, or you replace an existing technology that previously solved this problem with a new one. So the nature of your model, the interaction ways, and other decisions are usually unaffected. An example you used before to build and roll out your service by running shell commands. Now you introduce a tool that automatically builds, tests, and rolls out every time you merge a pull request. Let's look at both situations from the perspective of definition of done. Which artifacts do you need to provide to finalize, to say, I'm done with this decision? Let's first take the situation where you are making decision about a tool or technology. Here it looks simple. You deliver a document where you list all the requirements and constraints, list possible alternatives with their features, pros and cons, and finally list your option of choice and the main arguments for it. If as a data scientist you had to decide for, say, a library for training or for a tool for tracking experiments, this approach should sound familiar to you, only the technologies are different. Now we come to the situation where you are making the decision about how to integrate. Here is definition of done. You need to provide diagrams that reflect different views on your system. There are 4 diagrams I recommend you to master. Usually 2 or 3 of them are sufficient depending on the use case. First, the component diagram, your module, other modules you interact with, and interactions. Second, sequence diagram shows the interactions in chronological order. Third, you may need activity diagram if you have a multi-step flow with multiple paths. Here we have a flow of our data collection and model training. And finally, you need a deployment diagram. Here you show physical environment your model is running in, server or cloud service or container runtime or something else. You also define here the type of runtime artifact you are building, and you also draw in other components that you interact with. Why? Multiple diagrams are beneficial for decision making. To fully capture the integration, you need multiple views on it. From a structural perspective, from a behavioral perspective, from physical perspective. Only when you have created multiple views and the views are fit together and you have verified that none of the requirements and constraints are violated, you have a plan. Usually it takes several tries until you have a final version that is normal. For the 4 diagram types, I recommend getting familiar with unified modeling language. It is pretty easy and intuitive, and I have a book recommendation in the last part. Besides the diagram, you should create a document for each technology choice as described above. So we know what we need to produce as decision artifacts, but the part about making decisions is still missing. And you have to decide about components and interactions and technologies and tools and many other facets. For this, I would like to propose 2 strategies. They require different levels of technical experience for your team. And I call these strategies imitate and use ecosystem. Let's start with the one which requires a good technical background, the imitation. The gist of imitation strategy. Software development is not about inventing, it's more about adapting successful solutions that have worked in a similar context. So we need sources of inspiration. The first source of inspiration is the company you work at. Research what other teams are doing, not necessarily machine learning teams, even teams which are implementing a 100% declarative approach. Remember, no matter how unique and sophisticated your machine learning model is, you are not integrating a model. You are integrating a module that contains your model. Try to make your module as similar as possible to the modules that other teams deliver. Going back to our example, you have a scoring model to integrate. Okay, let's see what loan team is delivering. Okay, they are building a web service using Java programming language and using a Spring Boot framework, and they are using AWS RDS hosted database solution, and they are exposing RESTful API, and they are using JSON exchange format, and they have Kubernetes cluster for running their application, and they deploy with GitHub Actions, and they log their output into Elasticsearch database, and for monitoring the user Prometheus tool. Good. Let's look for another team, the fraud detection. So they implementing as web service as well. They are doing it in JavaScript instead of Java. And they are using a JavaScript framework. They are using a Postgres database, and the rest stays the same. We can do one thing, because as a data science team we are most likely familiar with Python ecosystem. Let's replace programming language and framework with Python and Flask, but keep the rest. So we can also deliver a web service and use the AWS storage and have all the other parts like two teams we considered before. If this solution fits your needs, this is clearly the way to go. Imitating others is also a good choice from another point of view. Infrastructure like runtime environment, deployment tools for logging and monitoring, and so on, are usually maintained by the platform team, which strives to have one solution for each problem and not several solutions. So the less specific requirements you have, the more likely you are to get the infrastructure you need. So the first idea, the first source of inspiration, imitate other teams from your company. Second source of inspiration for choosing the right technologies and tools, look at what community is using when facing similar challenges as you. The tools you should like, the tools you should look for should be modern and not outdated on the one hand, but on the other hand, mature and no longer in the alpha phase. The tools should be also widely used so that you can easily find many use cases, books, blog posts, examples, and a large community behind. Here I have some examples of such tools from 2021. If you need a workflow scheduler, consider Airflow. If you need relational database, consider Postgres or MySQL or Oracle. If you need a web framework, consider Flask or Fast API. So look what community is doing in similar contexts. So the third source where you can look for inspirations are design patterns. A software patterns is a general reusable solution to a common software design problem. A pattern usually has a name and a context that defines requirements and constraints, a solution description usually illustrated with diagrams, and a discussion section for benefits, drawbacks, and so on. Plus, sometimes a pattern has references to norm implementation. Patterns in general have been around in a software architecture since 1990s, and in recent years, a number of people have distilled patterns that are commonly used for machine learning solutions. Here is an example of one such pattern we consider a feature store. So for the feature store in the pattern catalog, you have a context. Many teams are doing machine learning work, many models in your enterprise using same or similar data, or engineering same or similar features. And the name of the pattern is feature store. And the solution is to have a centralized data collection and extraction of relevant features as a data engineering task, which you delegate to a data engineering team. And once you have a feature store built by this team, it should expose API for feature access and also provide metadata for feature discovery. And the benefits and trade-offs of these solutions is, of course, it solves the issue of reusing the work and and collecting and extracting features in a more solid way. It solves also the issue of training serving codes queue, because you can pull the features also not only for model training but also for serving, but it pays off generally for large number of models based on same data. So your enterprise should be big enough to um, to have a good ROI for the feature store. So this was one example pattern, and I recommend you familiarizing yourself with at least one pattern catalog. And here I have 2 links, and I hope we will also link them in the show notes. All the sources I listed where you can get ideas about integration scenarios, technologies, and tools give you options to choose from, but you need to make a choice. For solid choice, you need solid requirements to check if your plan covers them. You need experience, you need some creativity, and you need time. Only then the design you create will most likely be sustainable. Now let's consider another strategy which requires less technical expertise. The solution is generally to leverage existing platforms and ecosystems, which are mostly cloud services. Platforms and ecosystem cover the entire ML pipeline from raw data set to production by providing a tool for each stage and also allowing easy integration between stages. So when you choose a particular cloud service, you get a default option for pretty much all decisions. Take the example of Microsoft Azure ML Ops. Here you have solutions for data storage, for automatic pipeline training, for A/B testing, for experiment tracking tool, and so on. You can easily create a service out of your model and running in a scalable way, in a resilient way. You have built-in logging and monitoring. So for most of the requirements you have for a software system today, there is at least one good default option. Here I have listed some popular platforms and ecosystems that differ by features and use case they cover. Some are primarily for deep learning, some allow streaming data processing, some have good tools for analyzing data and models. So choose the platform which fits to your needs at most. And of course, you have to consider consider paying for them. And once you decide, you implement closely everything you need with the tools available in the platform. And hardly any tools in such platforms are standardized. So when you decide to move to another platform later, you get a different set of tools. You have to implement everything from new. So if we compare the two strategies, imitate and use ecosystem, you can see that the first strategy requires good engineering skills. You have a lot of decisions at the beginning, but also have to make decisions or replace existing decisions as you go along. Replacing a decision that turned out to be wrong is usually possible. The ecosystem strategy usually requires less architectural work and engineering background, and you should make a very thought out decisions at the beginning, and then you have mainly integration tasks. That was the part about making decisions. But there is also a second part: best practices, recipes, and tips. Some best practices for decision making. First, let's recall the problem we mentioned after. Remember the diversity of requirements. Even if your team does the best possible job in clarifying them, most likely some of your questions will remain not answered. Additionally, you're getting new requirements or existing ones will be changed. Experts estimate the number of changes by 2% in a month. Should you not start working until the last requirement will be clear and final? Usually there is no such option. Instead, you should learn to deal with uncertainty, and let me introduce you to some ideas what you can do. What I always try to find when gathering requirements are showstopper candidates. Some examples of them: team which has to integrate your solution has different goals. The only dataset you can use may not be licensed for your purpose. The infrastructure needed for training is not in place in your organization. If you identify showstoppers, this is for me the only reason not to start the project now, but to talk to managers and stakeholders for first explaining the risks and, if possible, make recommendations what they can do to get this resolved as soon as possible. And second, to discuss the option of working on something else instead that has a better chance of going live. If no good showstopper candidates are discovered, there are no more excuses to start working. But what about uncertainty? Here I have several ideas. First idea you can do nothing. Imagine you have your very first model and you have to retrain it every week. It would be nice if you had an automation tool for this, but you are not clear about further requirements and constraints for such a tool. So I recommend to do it manually as first. Later, when you have, say, 10 models, you will most likely know what an automation tool should be able to do. So you can postpone your decision. Second, what you can do, implement the simplest solution. Example, client application needs to authenticate to your service, but there are about 10 ways this can be implemented without any further clarifications which one. In this case, I would use HTTP basic authentication. With every web framework, you can implement it within a day. An advantage of this approach, if later the requirements become clear and you need to implement another protocol, no wasted time and no regrets about it. Third idea, designed for multiple options. If you do not know which one of possible options will be the case, such as, let's say, how many users your solution need to serve per day, you can make a decision that covers all the options. In this case, you can build your application to be scalable using load balancers, using cloud infrastructure, and working in a stateless way. Another example, if you do not know which cloud provider will be used by your company, and this is not your decision, but your company decides for one cloud provider for all the teams. You can package your application as a Docker image because every cloud provides a Docker runtime environment nowadays. So you can design for multiple options. Idea number 4, use standards and de facto standards. Example, you do not know how to design an API and which exchange format to take. Use REST and API as API design principle and JSON as the data exchange format. What is good about this, due to the wide popularity of both, integrating your API design such way will be easy for every client. So your counterparts will be happy to do it with minimal effort. So use standards and de facto standards. And the last idea, without any information, you can make an assumption that seems reasonable at the moment. You make a decision from that assumption and document it. Later, you go through the list of documented assumptions and check if they are still valid. If not, you also need to reconsider the linked decision. Example, at the day 1, you don't know how much your company is growing by month or by day, and you make an assumption that your company is growing by highest 1,000 customers a day, which which enables you to use particular hosting solution to host and run your ML services. And which this decision you calculate at least the next 5 years you can use this hosting solution. You document it, and in 6 months you review how fast your company is growing, and if your decision is still good, you can keep it. If not, if your company is growing faster, you may consider taking another decision. So these are ideas how to done with uncertainty. Now some more best practices for architecture. First, very important recommendation from my point of view, focus on interfaces, not internals. Once you gather requirements for your system, draw a component diagram where your system should be a black box and you only focus on others. Get as much information as you can about systems you depend on, not just technical details like data exchange formats, but also service level agreements like performance and throughput. And for external service, things like support terms and how quickly they fix problems. Once you start building your components, integrate the delivering systems as early as possible. Sometimes they do not work exactly as declared, and it's better to know that sooner than later, for asking for fixes, for implementing workarounds, for looking for alternative solutions. And considering the API you expose to other system, consider releasing those API as soon as well as a first version which responds with just dummy content. This way, you give your clients a chance to start integrating it and give you feedback on whether your API design meets their needs. And finally, once you are building your components, build them to tolerate failures from your suppliers. There are several design patterns for this, and I have a book recommendation in the last part on how to build systems that will not break in production. Essential practices how to survive failures from your suppliers are introducing fallbacks, isolating features so that parts of your components which are not depending on the failures can continue to work, and having meaningful logs. But in general, I strongly recommend you the Release It book of Michael Nygaard. I link this in the last part. So focus on your interfaces, not on your internals. Another recommendation: for every decision, there is an optimal time at which it should be made, and you should try to find it. This optimum is the result of two opposing forces. One is gaining information and options. You have more insights about the problem, your stakeholder makes certain decisions, the new solutions appear on the market. The other force is suffering from a missing or bad solution. Yeah, let me take the problem we looked at earlier as an example. You need a training automation tool. The later you decide, the more you know what automation features your models need, the more good the tool appears on the market. The earlier you decide, the more time you save with automation, the fewer mistakes you make doing manual work. Plus, you cannot make a decision if you do not have resources to implement it right now or soon. So look for the optimal time for each decision. And the last, it's perfectly fine to revise your decisions later. As we discussed, new information comes from the business, you get new insights from your work, and new solutions come to market, or the old solutions are no longer supported. So at some point, every decision you make today becomes suboptimal. So do not design for into eternity. My personal rule of thumb is that a decision I make today should be sustainable the next 18 to 36 months. The number depends on your business. Some businesses evolve faster than others, and they depend on market and industry and few other factors. That's it about decision making. But a decision that is not shared is meaningless. In the next part, we'll talk about communication and documentation. And there is a part about personal development, how a data scientist can grow into architecture. Thank you for your interest in the topic.